Okay, modeling essentials. Now that we understand where we are, let's build from here and try to do as best as we can. But please do not think for a second that you have modeled the structure accurately and now you can predict everything and you know everything what you're doing, because you don't. Okay? That's why engineering judgment understanding is very important, to know what you know and also to know what you don't know and to make account for those things. That's the key. You know something that you haven't done properly, but you also know how to cover it up properly. So not ignorance, is kind of a, I would say, controlled ignorance, you can say. That's why we have the factor of safety to cover for that. Okay, first of all, going back now to a continuum, the difference between continuum and how we see things. And that's the main difference. Why? The first step is this one. A mechanical engineer, a heart surgeon or heart modeler, or somebody modeling the tooth, see the continuum as it is. They don't simplify it. They say they try to keep it what they have as it is. We simplify it. Based on continuum, we put them XYZ dimensions. First of all, heart has no dimensions, correct? There's no length, height, width, no thickness, no nothing, right? It is what it is. So as soon as you put dimensions into something, that means you have already moved away from reality. And then we further say, okay, this is a plate and this is a beam. Because if you say, okay, this is a solid XYZ, but if suppose the thickness is too small compared to other two dimensions, I will call it a slab. And then I will design and model it differently from if it was very thick. And where is that line drawn? Arbitrarily. And then if we say if the length of the thing is too long and other two dimensions are small, I will call it a beam. Even though it is the same solid, just the dimensions are different. So we start calling them by different object types. And then everything from there changes. We start following different rules for design of slabs or plates. We start following different rules for the design of beams, and then different for trusses and struts and so on. Just because we look at their geometry and start making decisions. That doesn't happen in mechanical engineering. For them, a solid piece is a piece, always is a product, is a piece. It's always modeled with solid elements, no matter what. And they will analyze it, stresses based on that model. Only one model. They will not simplify it. And that's one of the main problem that we have, that we immediately start to think about the dimensional thing and then start to get into the problem. This is a deep beam. This is not a deep beam. This is a thin slab. This is a thick slab. This is a footing. And then we say, oh my God, what do I do now? And this is a column, this is a beam. This is a column, this is a beam. What do I do here? We are confused because we start making these arbitrary distinctions between that. So this is the start of the problem, that we do this. But this is what we do. Okay, so we do continuum to regular to plate shell idea, and then frame or a beam. This is the first problem that we create for ourselves, but this is the first modeling decision you'll have to make. Which category are you going to pick from this? Because rest will follow from there. So based on what you pick, you have the option of representing them as line elements, or you have the option of representing them as surface element, or you have the option to representing them as solid elements, volume elements. So these are the three kinds of finite elements, behavioral models that we can choose from. One is that if the length is very long and the dimensions are small, then we take the length as the primary modeling parameter. If this one, we take two directions, x and y, as the modeling, and t is a property. So here length is modeled, cross-section becomes a property. So that means the line element, this one, doesn't care whether it is a big one or thin one, it's always the frame. So that's why I say, if the beam is very large, is it justified to create a beam, and very short? We come to the problem of deep beam that we studied. Same thing here. So we say this is so for us, this one and this one, both are shell. But if this one become like this one, Is it shell or should it be solid now because it's too thick, right? So you can see these three things are three different thickness ratios, right? Is this plate or shell? What about this one? And what about this one? So we just say, oh, this one is now solid because it's very thick. This one, I don't know, still plate or shell. This is, I'm sure it's shell, right? That's how we make decisions. So that's the plate shell elements. And that's the tetrahedron. Most other fields only use solids because this captures everything correctly. Rarely they will use shell, but never this. But we always start with this and almost never use this. So that's how that's why our thinking in finite element is so limited. So this is a typical building. Solid elements, some people can use. Of course, normally people will not use, but we should use because it's a thick raft there. So it's a solid. Then we use shell elements here, and then we use and then we have the frame elements. So you can use number of different elements in the same structure so when I say dimension of the element is 1D, 2D, and 3D, not the structure. Structure is always 3D generally, but the element representation is either 1D, that means only one dimension is modeled, the other two are properties. 2D means that two dimensions are modeled, third one is a property. 3D means all three dimensions are modeled, there is no property. So when you use solid element, it has no property. No moment of inertia, no thickness, nothing like that. So same structure, a table like this one or that one, that table over there, you could model in a number of ways. You could model it as a solid model. This is what a mechanical engineers will do. Just create as it is. All these small things, they just take the CAD drawing, CAD model, manufacturing CAD model, and then just convert the finite element from there automatically. So the finite element model is exactly the same as the manufacturing model. There is no difference between the two. But in our case, no, we will ignore all these small things, the footings and everything, and we will model it and then put some pin supports. So this is the solid model, the full reality. This is the shell frame model where we'll say this one is shell and this one is frame because these are long and this one is thin. So we can say, okay, I'm going to use the frame model and the slab will be converted into T-beam or L-beam property. Slab, I will calculate the load from slab and I will apply to the frame. So we create a open frame model, which we used to do a lot. Or just 2D frame, just convert it into 4 frames, analyze them separately. Or just take the top and put it on 4 supports and analyze it for the slab. So this is how our simplifications can convert a real structure into 1, 2, 3, 4, 5 different models. So now what's the problem here? Let me ask you this question. These 5 models, will they give you the same answer? Same response? Everybody saying no. Then the question is, which one is the right one? Yeah, but then I will say, but this is concrete. It's going to crack. How are you going to incorporate the cracking of concrete in a solid model? The AEM is the answer to this problem. But of course, AEM is its own issues, but that's a separate part. But I agree with that. I'm actually of the same opinion that we have to go to that direction if we want to have our structures fully modeled as other people are doing. What would I do with the cracking? So then you have to keep changing the model by connecting the solid elements by nonlinear link, which keep opening and cracking. So very complicated. Once we tried, we tried to create a finite element solid model for a brick wall, by modeling each brick as a separate solid element connected to other bricks through those nonlinear link elements, which will break, and similar to what AEM is doing. But we try to accomplish that in finite element. At that time, just one wall exhausts the memory, the capacity of the software, because there were so many elements there, so many connections. So practically, this model will be very, very large, number one. But more importantly, it will give you the results that building codes do not recognize, because there is no bending moment coming out of this one. Right? There is no shear force coming out of this one. There is no torsion coming out of this one. All your design codes are written on bending moment, shear, and torsion. What will you do with the results? So that's the problem here. Of course, this is very good for response, but not for design at the moment. Mechanical engineers use ANSYS. They don't use SAP. ANSYS has very, very comprehensive material models, so complicated that you cannot even imagine. So they can model heart, muscles, and other things. Models which has 70 properties, not 2, 3 properties, right? So anyway, which is the next best model? This is the current choice of ETABS and other people. They model this slab by shell element and columns by frame element. So this is our best approximation at the moment because it gives you what we need. This is what we used to do and this is what ETABS used to do before they had shell element, which was not long ago. And then this is what we used to do when AIT developed 2 programs called Microfeep P2 and P1. P1 was a frame 2D analysis, P2 was a grid analysis. Do you know that the Don Mueang tollway was analyzed using these 2 programs? The one going from Don Mueang Airport to the city, those bridges were analyzed using Microfeep at AIT because at that time they were very good. So they divided the structure into 2 separate parts, deck separate, use P2, and frames separate, use P1. Manually combine the results together. Transfer the results from deck to the frame, analyze the frame. And that's how we used to do earlier. So depending upon the tools that you have, depending upon what you want from the structure, you can choose any one of those models, each with its own data, limitations, and all. Right? But these 2 models had the big advantage. Engineering was the key, not the tool. You have to understand how you are going to convert the structure into 2 separate. You have to understand how the load transfer happens. You have to understand everything, and you assemble the things by yourself. It's like Lego. You get the pieces, you know how to put them together, and then you can also buy a model car, but you don't know how it was made. But this Lego pieces you can disassemble, and you understand fully how it is put together. So that was the Lego, style modeling, where you do pieces and then put them together. Now, fortunately or unfortunately, we have that when we don't know at all what we're doing. So we come back to this, going to discuss more details about these modeling techniques and when we choose this one, when we choose this one, when we choose this one, or this one, what are the differences and how do we create all these models realistically? The first thing is we start with zero-dimensional element. You will say, what is a zero-dimensional element? Zero-dimensional means that it has no dimension. It's a virtual element. It does not really exist, but we create a kind of a notion that there is something called a node. And node is defined by the coordinates and the degrees of freedom. Previously, nodes used to be represented mostly like this one, and you put a circle here, circle here, circle here, circle here, and we call it node. And people thought that this circle is enough. But then when the computational technologies developed, I saw first time our professor at that time in AIT, Professor Warsak, he used to draw nodes as squares, not as circles. And later we realized why he was doing that, because when you deflect this one like this one, this will rotate. The node will rotate, and then it will tell you how this will reflect. Because at the joint, members have to remain perpendicular, 90 degrees. So it was a very good way to quickly visualize the deformation of a structure, because if you start with square node, the node should remain square after deformation, and all members entering the node must remain at 90 degrees. So that can automatically give you a very good idea how the members will deform. But more importantly, the joint has its own coordinate system, which is different from the global. So joint has a local coordinate system also. And you will wonder why that is the case. And its first application is very long time ago, and I was trying to design something on an applied plane, inclined space. And then if you now put the foundation, building is like this, now the foundation, if it is inclined on this one, then you have a problem because this is not the same as a foundation like this. The behavior will not be the same. But for the round thing is the same. But this thingy will slide, but the round thing cannot detect that. So that means this point should have its own local axis where I want it, where I want it supposed to be. So this is the roller, but it will slide on the plane like this one, not like this one. So this roller is sliding here, and that this is global x and y. But this one has to be rotated. This is x and y, but the joint degrees of freedom must be rotated so it can move in a certain direction, not in the direction. So that's the reason that the local coordinate system of the joint was introduced. So which means that now we have the local coordinate system also of the joint. And so we have 6 degrees of freedom at the joint, 3 displacements, 3 rotations, and 7 degrees of freedom. The warping is at member level. It's not at the joint level. So then the problem is that this joint can be rotated in any direction. So there are 3 axes. So you can rotate it on this and then like this and then like this. So order of rotation becomes very important because depending upon whether you rotate about x first, then y and then z, or z first, then x and then y, because then you will end up with different configurations. So the order of rotation for the joints for local axis and the angles have to be done like this one. So step number 1, about 3, then about 2, then about 1. That's the order how we rotate, but you can all rotate in any way. So every rotation will produce different results. So what I'm trying to explain to you is that do not assume the joints to have the same direction as x, y, z. So that kind of thing, you should understand that you must consciously assign the local coordinate system for the nodes, and you are able to rotate them at will. And that will change the results, change the boundary conditions. That's the first important point. Then we come to one-dimensional elements. We have seen these pictures in the last course. So one-dimensional element is that the element is along any direction, only length. This is one-dimensional element. Only length is a dimension. Other 2 are properties assigned to the line. So it's a one-dimensional element, but doesn't mean it will live in one-dimensional space. Space is always 3-dimensional, but the element could be 0-dimensional or element could be 1-dimensional like this one. So if you have one-dimensional element, then its properties have to be oriented about 2, 3, because major properties, minor properties, which direction, how do you put the ix and iy? So that's why you remember we had this member axis, we have these 7 degrees of freedom, and we talked about them in the last course. And then we had those deformations, properties, and forces around 6 directions. So we studied this in last course, and I told you at that time we'll come back to this. And today we come back to this because now we need to deal with local axis, very important in the analysis, because sense of bending moment will change. So for example, this way, moment of inertia is very different from this direction. So if you do not orient it properly, you will be designing the wrong direction, or you will be putting you think you have put the ruler like this, but it could actually be like this if you do not fix the local axis properly. So everything will be wrong. So fixing the local axis is very important. Now in ETABS and others, you can use the extruded view to check. Previously, there used to be no extruded view. So you could never know how the axes are located. So anyway, so that's the second important thing, that when we do the one-dimensional element, and you remember this thing. So if you cut that, I told you about the local axis like that. And we talked about the rule. We talked about the right-hand rule and how they are oriented. So the decision that z is up up is arbitrary. In some programs, y is up, and in some program, x is up. So it doesn't matter. You can actually, when you use e-tabs, you can decide what is up, what is down, what is left, because it's all arbitrary. Just you need three axes, and then you organize them. All of them are perpendicular. Their order is important because their sense is important because of the moment and rotations and all. So understanding the axes will be very critical if you want to now move to the ETABS results and understand how they work. So local axis, the same way you can place. So global axis, local axis, understanding of their orientation, all of that, you must be very careful. Otherwise, your results will mean nothing. And this one is always the cross product of the two vectors. So math, I think vector math is so useful in dealing with coordinates. And you remember this video. So the local axes go together with the member,